Hello, everyone. Welcome back. Today, we're going to be talking about repeated sampling and hypothesis testing. So, let's do some reading first. It says if a sample of size n is taken from a normal population, then sample means x bar from a normal distribution with the population mean mu and the standard deviation sigma are also normally distributed and have mean mu and have a standard deviation of mu of sigma over root n. So what's this trying to express to us? They're trying to express to us that when we have a normal distribution, if we take the means of the normal distribution, right, we repeatedly sample up the population over and over and over again, we're going to end up with something like this, right? We're going to end up with something that looks like this, a distribution of the sample means, which is also a normal distribution as well, except the new standard deviation is going to be sigma over root n, rather than in this one where the standard deviation is sigma. So that's really what they're trying to tell us here. So I just wanted to kind of clarify that as to what are they telling us. They're telling us that the mu would be the same, but the standard deviation changed. It becomes smaller because now we're taking we're taking all the all the different samples, and we're putting them on a we're continuing to we're repeatedly sampling here, and we're putting them on a chart. Now let's talk about what is hypothesis testing. Now this is different from hypothesis testing in science class. This is a new type of hypothesis testing that has to do with statistics. Basically, hypothesis testing is to assume the truth of the null hypothesis, which is HO, and that comes from the population information, and then investigate an alternative hypothesis, which is H1, or sometimes people say HA as well, and that comes from the sample information. Now, the significance level is the probability of error which the researcher is willing to accept for the alternate hypothesis, or the amount of probability the researcher is willing to accept that H1 is incorrect, right? Because reality is we're not going to get exactly the same thing when we do a sample versus the population, but how close would we have to be to be able to assume we're correct, right? How much error is an okay amount of error versus how much error is not okay, is too much error for us to really say that these results are accurate, right? What do we have to do exactly to reject the null hypothesis and say the alternate hypothesis is good, right? Okay. Now that brings us into confidence level. So 1 minus alpha is the probability amount needed to accept that the alternate hypothesis is correct, and that therefore the first hypothesis, the null hypothesis, we can reject it. It's not correct. One thing I want to mention too is that we can never actually accept the null hypothesis. We can only reject it or fail to reject. So either we're not sure if it's correct or not, so we're not going to reject it because we don't really know, or we can know, okay, yes, we're going to reject it. We're never going to accept the null hypothesis. However, we can accept the alternate hypothesis. That is possible. Okay. So let's go ahead and do this example. It says, example 1, a food company produces sweet potato fries with a label on the bag stating it weighs 850 grams. The company claims that the weights are normally distributed with a mean of 850 grams and a standard deviation of 15 grams. A quality control research team purchases 20 bags of sweet potato chips or fries, and they are found to have a mean mass of 845 grams. Create a hypothesis test of the company's claim with a significance level of alpha is equal to 5%. Okay, so let's go ahead and do that. So first of all, what's step 1? Step 1 is I'm going to state my hypotheses. So what is my HO? And what is my H1? Well, let's go back to the definition because I just introduced them. We're not really familiar with them yet. It says to assume the truth of the null hypothesis, which comes from population information. So this has to do with the claim that the food company makes. The food company is claiming that mu is 850 grams, right? However, the research team found out, they purchased 20 bags of sweet potato chips, and they said, oh, the mean is 845. So what we're trying to figure out is the fact that the research team did this, is this off enough that we can conclude that the alternate hypothesis is correct, that mu is actually not 850, that this company is lying to us or this company is incorrect in some way, or maybe this number is close enough that this is a sample that we're relatively likely enough to get, and so they're not lying to us, and we're good, or at least that there's not enough information to prove that they are lying to us, right? Again, we can't accept the null hypothesis, but we might fail to reject it, right? So let's go ahead and continue the question now that we understand the hypothesis. So we're trying to figure out, can we reject the null and accept the alternate hypothesis that actually the food company is lying to us or doesn't have very good measuring tools and is actually gypping us of our chips? Or is there not enough evidence based on the research team's study to prove that? Okay. Now, what about standard deviation? So, standard deviation is 15, we said. And the sample mean, right, from this sample of 20 is 845. Okay, so in that case, what is our standard deviation of our sample? Well, that's going to be 15 over root 20, right? Actually, something else I should mention here is n is 20. So I'm going to slow down, hold my horse a little bit. So sigma being 15, we got from the question. N being 20, we got from the question, right? Because there's 20 bags of chips we're testing, and N is just the number of trials we're doing. And then X bar, same kind of thing. I got it from that. That's a sample mean. So what's our sample standard deviation then? Well, that's going to be 15 over root 20, which is 3.36, right? Okay, so now what we're going to do is we're going to find the z-score. So the z-score is going to be the sample mean minus the population mean over the standard deviation of with respect to x, right, of our sample here specifically. So the standard deviation is this standard deviation, right, the distribution of sample means, that standard deviation, as opposed to our original standard deviation, because we're trying to find out, how likely is this to actually be one of the samples here if this claim is true. So let's go ahead and do that. So this is going to be equal to 845 minus 850 over the standard deviation, which actually I should plug in right away, is 3.36. So that's equal to, if we plug that in our calculator, negative 1.49. So now I would like to know what is the percentage that would happen, right? The probability that X bar is less than 850, right, in any given trial we're doing of 20, is equal to the probability that the z-score is less than negative 1.49, which is equal to, let's see, we don't know this part, we need to go find out. So negative 1.49 is our number we're searching for. All right, so here's negative 1.4, and negative 1.49 is all the way over here. So the answer is 0.0681. Okay. 0.0681, which is equal to 6.81% if we put that in percentage form. Now that is greater than 5%, and it said that we're testing this claim with a 5% significance level, right? So we're going to see, is there a 5%, not chance, but, a 5%, 5% certainty here, or 5% confidence, we could say, that this is going to be the case, or no. And actually, as it turns out, 6.81, our probability is greater than 5%. So what we're saying here is there's a 6.81% confidence that this is the case, which is greater than our 5%. So therefore, we will reject our alternate hypothesis. We will reject H1, right? And therefore, we will fail to reject our original hypothesis. So basically, what this means, I want to make sure we understand that this does not mean that the mean appears to be 850. Okay, this does not mean the null hypothesis is correct, but what this means is that there is not enough evidence. There is not enough evidence for a 5% confidence level, at least. There is not enough evidence that mu is less than 850, right? There is not enough evidence that mu is less than 850, or we can say, in other words, that H1 is true, right? There's just not enough evidence of that. So maybe, maybe it's true that mu is actually not 850, but we don't have enough confidence in that to make that claim, right? And let's say we were doing this in real life, right? Because in a lot of these questions, it'll just be, a 5% significance level is a pretty common one. However, for like a company to actually do a lawsuit, it would have to be way less than that. It would have to be, a very, very small percentage chance that, that a food company is lying to us in order for there to actually be some real lawsuit here. And so in this case, it's not that unlikely. It's not unlikely enough that we're going to want to make this claim that this food company is not being honest. And so we're going to fail to reject that hypothesis, the null hypothesis. Okay, good. Let's move on to another one. So before we do that, though, these next ones have to do with the normal approximation to the binomial distribution and the confidence levels as well. So just a quick reminder on that. We did this as our very last lesson, so hopefully this is nice and fresh, that if a binomial distribution is graphed and it satisfies the following conditions, that NP is greater than 5 and also NQ is greater than 5, then it will be like a normal distribution. We also know that a normal distribution would have the same approximately as the binomial distributions would have. So mu would be approximately n times p, which makes sense because that's our expected value. And the expected value is the mean value we're expecting to get. And then standard deviation would be the square root of npq. Okay, so with that little review out of the way, let's move on to example 2. Example 2 says a drug company is testing a new flu vaccine on 200 people. Typically, on an average year, 12% of the human population gets the flu. Of the 200 people given the vaccine, 17 people get the flu. Right? So if we think about it, well, that's if it's 200 people and 17 are getting the flu still, then that's less than 12%, right? Because if it was 12%, 24 people out of that 200 on average would get the flu. So here it says test the significance of this study with a significance level of 10% and consider if this new flu vaccine is effective. Okay, so to do that, I'm first going to write out our hypotheses. So our null hypothesis is that the probability is equal to 0.12 or 12%, right? That we have 12%. And then our alternate hypothesis would be what? Our alternate hypothesis is the probability is less than 12%, right? We're trying to test this and see, with this vaccine, is this still true? Or maybe now it's true that, that less people are getting the flu. So is the fact that only 17 people instead of 24 people in this case got the flu, is that enough evidence to suggest that this vaccine is effective and that people who want to avoid the flu should get this vaccine? Or is the 17 people, only 17 instead of 24 people getting the flu likely enough, just even without the vaccine, that this vaccine isn't very effective and this drug company should continue to work harder to produce better vaccines that are more effective for everyone? So that's the question we are wanting to find out for this example. Okay, so we need to find mu and sigma. So just a reminder, n is equal to 200 because we have 200 people. N is equal to 0.12, right? Or sorry, P is equal to 0.12 because the probability of one person having the flu is 12%. And then Q would be the other 88% of people who do not get the flu, even, whether or not they have the vaccine, right? On just a typical year, before this vaccine has come into play. So mu would be NP, which is 200 times 0.12, which is 24 people, right? The expected number of people to get the flu, if we're testing on 200 people, is about 24 of those people would get the flu. Standard deviation would be NPQ, NPQ, which is 24 times 0.88, which is what? I don't know. Let's type that in. 4.6. Good. Okay. So X is going to be 17 because we want to know, do 17 people get this flu? Right? Is the fact that 17 people got the flu out of the 200, is this evidence enough with a 10% confidence level that this vaccine is effective to us? So let's do that. Let's find the Z score now. Z, as a reminder, is equal to X minus mu over standard deviation, which is going to be 17. So our sample mean minus our overall population expected value mean, which is 24, over standard deviation, which is 4.6. And then we have negative 1.41 as our Z score. So what does this mean? This means that the probability that we have less than 17.5 is equal to the probability that the Z score must be less than negative 1.41, which is what? Well, we have to go and look back here and figure it out. So what is the Z score? Negative 1.41. So that's going to be here. That's going to be 0.793. Okay. 0.0793, which is about 7.93%. Now, unfortunately, 7.93%, that's less than 10%, which is the confidence level we needed. So we're only 7.93% confident about this. We are not up to that 10% confident. So therefore, we need to reject HO, right? And so therefore, it appears here that the vaccine lowers the flu at a significance level of 10%. So if that's the confidence level we want to have, then this vaccine is good enough. There was enough evidence here, enough of a difference between the number 17 and the number 24 to suggest to us that the vaccine does help out. Now, is the vaccine 100% effective here? Well, no, right? Still 17 people got the flu, but we would have expected without the vaccine for 24 people to get the flu. All right, so there we go. Okay, let's do example 3. It says here a coin is flipped, where flipping a head is considered a success And of course, I guess flipping a tail would be considered a failure then in this situation. After flipping a coin 36 times, 22 heads were recorded. Test the significance of this result with confidence level 90% and consider if this is a fair coin. So if our confidence level is 10%, or is 90%, I want to just point out that means our alpha value is 10%. So same as the last one, because confidence level and significance level, we just do one subtracted from the other in order to find the other one because they're opposites. Good. Okay, but other than that, the first thing we need to do is to state our hypotheses. So what is our null hypothesis and what is our alternate hypothesis? So our null hypothesis is that the probability is 0.5, right? That's what we're expecting. We're expecting the probability to be 0.5. However, after flipping 36 coins, we got 22 heads, whereas we were expecting to only get 18, right? If the probability of getting a head once is a half, right? We'd expect 18 of the flips to be heads and 18 to be tails. So we're going to try and test whether or not this is a fair coin in this situation. Is it likely, right, that probability is actually greater than a half, given that we happen to flip 22 heads? Or is this a common enough occurrence that's going to happen sometimes to where the coin, it could still be a fair coin? Okay, so let's figure it out. Well, first of all, P is equal to 0.5 and Q is equal to 0.5, right? Because the probability of success of a head being flipped is 0.5, and so is the probability of a tails being flipped, which is also 0.5, n is equal to 36 because we flipped these coins 36 times, or this coin 36 times. So mu is equal to n times p, which is 0.5 times 36, which is 18, right? We're expecting to get 18 um, successes, 18 head flips. Now, what's our standard deviation? Let's see. That's going to be root of npq. That's going to be 36. Let's see. That's going to be root 9, which is 3. Okay, so our standard deviation is 3, and our x value we're testing is 22. We want to know, is it, just a coincidence? Is it possible that this is just a coincidence that we got 22 heads this time? Or is this evidence with a 90% confidence level, right, and a 10% significance level that the coin is not a fair coin and actually it does flip more heads, on a regular basis? But that is, theoretically what it's going to do. So let's see. Let's see. So we want to know what's the, actually, first we got to know the Z score. So the Z score is going to be equal to 22 minus 18 over 3, which is 4 over 3. Let's see. Wait, actually, I'm doing this incorrectly. My apologies. So this is not continuous. This is discrete. So actually, a stronger way to do this would actually be to say 21.5 rather than 22 minus 18. So that's going to be a little bit stronger. So let's do it that way. Divide by 3 is going to get us 1.17 for our Z score. Okay, so then that means the probability that x is greater than 21.5 is equal to 1 minus the probability of x being less than 21.5, which is equal to 1 minus the probability that our Z score is 1.17. So that's going to be 1 minus whatever that is. So let's go find 1.17 on our chart. Here is 1.17, which is 0.879. which is 0.121, right? So 12%. So 12.1% is greater than 10%. So therefore, what do we do? We're going to reject the null hypothesis, right? And we're going to say, or sorry, we're going to fail to reject. My apologies. We're going to fail to reject our null hypothesis. So basically, there is not enough evidence to suggest that the coin is an unfair coin. Now, that doesn't necessarily mean that it is a fair coin, so I wouldn't say conclusion it's a fair coin, but what I would say is that there is not enough evidence to strongly suggest to us, based on this confidence level, that it is not a fair coin. So it may be a fair coin, it may not be, but based on the data we collected, we don't have enough evidence to say for sure that, oh, it's actually not a fair coin, and to accept our alternative hypothesis. Okay, so we're going to fail to reject the null hypothesis. The null hypothesis may be true. All right, well, that is it for our hypothesis testing. There will be way more. There is way more to this topic than just these few kinds of examples that we will do moving forward into the future. Okay, so do make sure that this is something you keep in mind, because this is something that will come up later and later, more and more in statistics. So if you do take any sort of university statistics, this is certainly something that will come up again. In terms of how far we're going to get into it in this course, I think we're going to stop here. As this is not, this is a very large can of worms that we're not going to tackle all of right now, but there is a lot more to learn about hypothesis testing moving forward into your future. All right, so that said, that is it for today's class. Next time, we're going to be talking a bit more about confidence intervals, and that's actually going to be our very last lesson of this entire course, is confidence intervals. So good work today, everyone, and I will see you next day to talk about confidence intervals. Bye, everyone.